Here I'd like to present my thought process towards the diagonalization of a rotation matrix. So as you might know, or as we'll see in this video, rotation matrices are not diagonalizable over real numbers, but they are diagonalizable over complex numbers. And I think I have a nice way of visualizing that diagonalization process, which, like I said, I'd like to go over. And if you want more linear algebra stuff, I'm making a full course. In fact, the full course may be almost done or done by the time this video is out. And that's happening at the second Math Major channel. So check a link in the description. Okay, so we're going to start with this rotation matrix. I've called it R theta. And it's a 2x2 matrix. So I mean a rotation matrix in 2 dimensions, given with entries cos theta minus sine theta, and cosine theta. So the first thing that we'd like to do is get some intuition for what this matrix does. So I've called it a rotation matrix. So probably it rotates things without expanding them, but let's just check that in a detailed manner just to be sure. Okay, so let's look at the real plane. So in other words, R2. So here's R2. And let's take an arbitrary vector in R2. So I'll put that arbitrary vector in the first quadrant, but it could really be anywhere. So let's call that vector V. And then let's say that vector has components x and y. And so that means if I project onto the horizontal axis, I have a value of x. And if I project onto the vertical axis, I have a value of y. That means I can write this in the standard basis as x, y, in the column form. Okay, so now we want to investigate, like I said, the action of r theta on this vector. So let's look at r theta times this vector. But that's going to give us cos theta minus sine theta. Then we have sine theta, cos theta, times our vector x comma y. Now we need to do matrix multiplication to see what we get. Or maybe I should say matrix vector multiplication. So if you recall how we do this, we take our first row here, then we swivel it into this column vector. Everything that kind of lands on top of each other, we multiply and then we add. So that's going to give us x times cos theta minus y times sine theta. So something like that. So that'll give us x times sine theta plus y times cos theta. So something like that. Now we'd like to compare this final vector with this starting vector. Maybe let's start by measuring their norm to see if the length of each vector has changed. So let's calculate the norm of v, which will be the square root of x squared plus y squared, just by the definition of the norm. But now if we take the norm of r theta times v, that'll give us the square root of x times cosine theta. So x times cos theta minus y times sine theta quantity squared, and then plus x times sine theta plus y times cosine theta quantity squared, like that. But now let's see what we get when we multiply this out. So multiplying this out will give us x squared cosine squared theta minus 2xy cosine theta sine theta plus y squared sine squared theta. Okay, so that looks kind of interesting. And then multiplying this out will give us x squared sine squared theta plus 2xy cos theta sine theta, and then finally plus y squared cosine squared theta. But now we can start adding things together. So notice this x squared cosine squared will add with this x squared sine squared and just give us x squared. Because we know cosine squared plus sine squared is 1. We also have a similar happening with this y squared sine squared and this y squared cosine squared. So that gives us plus y squared. And then finally, we'll see that we have a minus 2xy times some stuff and a plus 2xy times the same stuff. So those cancel. So in the end, we have the norm has not changed. So that means when we draw this new vector up here, it will have the same length. So let's maybe go ahead and draw it up, giving it the same length. Maybe we'll put a little hatch here to show that it has the same length. And the next thing that we'd like to do is measure the angle between those vectors just to get a real feel for what's going on. Of course, we've called this a rotation matrix with this angle theta, so we suspect this angle is theta, but we'll check that for sure. So maybe just to save for the next step, I'll just put our result here. So the norm of V is the same thing as the norm of r theta times V. Now let's get rid of this calculation and then we'll calculate the angle between these two vectors. So we just determined that our matrix r theta does not change the norm of a vector. So that means the input and the output have the same length. Now we want to see the angle difference between the input and the output. And so let's maybe set phi equal to the angle between, we'll say V and r theta times V. But let's recall we've got a nice result as to the angle between two vectors and a formula involving the dot product. In particular, we have cosine of phi equals V dot r theta times V over the modulus of V times the modulus of r theta of V. Okay, nice. So now let's do this calculation. So first up, we know that the modulus of V, the modulus of r theta times V, were both the square root of x squared plus y squared. So that means when we multiply them together, we get x squared plus y squared. Now let's see what we get when we dot V into r theta V. That means we multiply this component by x, this component by y, and then add them. So that'll give us something like this. X squared cos theta minus xy sine theta. And then we'll have plus xy sine theta. Again, we multiplied this by x, this by y. Again, that's just by the definition of the dot product. Plus y squared cosine theta. Okay, nice. Now let's notice that some stuff cancels out, like this and this. And then we can also factor a cosine theta out of the numerator. That gives me cosine theta times x squared plus y squared over x squared plus y squared. But some more stuff cancels, this x squared plus y squared, and we end up with cosine theta. So we've got cosine of phi is equal to cosine theta. In other words, the cosine of the angle between V and r theta V is equal to the cosine of our angle. But that being said, theta here can be taken between 0 and 2 pi, not including 2 pi. And so that means that phi is equal to theta because on that region, the cosine function is injective or 1-to-1. So via that argument, we have that this angle right here is theta. Okay, nice. So what we've done is determine that our rotation matrix indeed does exactly what it should do, and that is take a vector and rotate it by theta degrees or radians, however you measure it, counterclockwise, and it doesn't do anything to the length of the vector. Okay, so now let's work on diagonalizing this matrix and then looking at a visualization trick for that diagonalization. So we just looked at the geometric interpretation of the action of this matrix on an arbitrary vector. Now what we'd like to do is diagonalize this matrix. As we'll see, we can't do it over the real numbers, but we can do it over the complex numbers. But let's recall that if we want to diagonalize this matrix, we need to know its eigenvalues and eigenvectors. So let's find those right now. Finding eigenvectors and eigenvalues starts with looking at the characteristic polynomial. So we'll call that P r theta x. And let's recall that that is the determinant of x times the identity matrix times r theta. Sometimes that's written in reverse, but that gives you the same kind of thing. So we want to look for the roots of this. The roots of this polynomial will in fact be the eigenvalues. So again, if you want a refresher on eigenvectors and eigenvalues, check out the other channel. Okay, So that will be the determinant, which I'll just write with these lines around a 2 by 2 matrix of, let's see, we have x minus cos theta here, and then we have sine theta here. Then down here we have minus sine theta, and then another x minus cos theta like that. Okay, looking good. Now we'll do the standard rule for the determinant of a 2 by 2. So it's the diagonal terms multiplied, the off diagonal terms multiplied, and the difference. So that'll give us x minus cos theta squared. And then let's see, plus sine squared theta. So something that looks like that. So let's multiply that out. That'll give me x squared minus 2 cos theta times x. So that's my cross term here. And then I'll have plus cosine squared plus sine squared, but that's exactly plus 1. Now we, like I said, like to find the roots of that. So we can find the roots of that by using the quadratic formula. So let's see, x will be equal to negative b, so that'll be 2 cos theta plus minus the square root of b squared minus 4ac. So let's see, our b squared term here will be 4 cosine squared theta minus 4ac will be minus 1 times 4, so minus 4. This is going to be all over 2. Again, quadratic formula. Okay, so next up we can notice that 4 times cosine squared minus 4 is exactly negative 4 times sine squared using the Pythagorean identity for cosine and sine. Okay, but now we can maybe take this 2, cancel with this 2, give us cosine theta, and then we'll have plus minus. Well, we need to take the square root of negative 4 sine squared. That'll give us an I and a 2, which can cancel with this 2, and then times sine theta. So we have cos theta plus I sine theta, but we can rewrite that as e to the I theta. Well, maybe plus minus I theta. So we have 2 eigenvalues, e to the I theta and e to the minus I theta. Okay, so let's maybe take that data to the top, then we'll find the eigenvectors. We just found the 2 eigenvalues. They were e to the I theta and e to the minus I theta. I've renamed that lambda plus and lambda minus. Now we need to find the eigenvectors. So that involves looking at a certain null space. So the eigenspace for lambda 1 will be equal to the null space of lambda 1 times the identity matrix minus r theta. Okay, so again, if you need a refresher, we got a course over here. So let's maybe do that calculation. That will be equal to the null space of, let's see, we'll have a lambda, I should have lambda plus here. I guess I'm using that notation. Lambda plus minus cosine theta up here. And here we'll have a sine theta, a minus sine theta, and then finally a lambda plus minus another cosine theta right here. So that's what we have for our matrix. But now let's use the fact that lambda plus is e to the I theta, which can be rewritten with its expansion as cosine theta plus I sine theta, and then that allows us to simplify some things. So I'll cut out one of those steps, and we'll just notice that in this entry, we'll have I times sine theta. Here we'll have sine theta. Here we'll have minus sine theta, and here we'll have I times sine theta. So something like that. But now let's recall that the null space of a matrix does not change when you row reduce it. So we'll row reduce this. First thing that we can do is divide both rows by sine theta. This is a little bit problematic if sine is equal to 0, but we'll just assume that sine is not equal to 0. Okay, so that'll give us the null space of the matrix I1 minus 1I. Okay, so that's starting to look good. Now let's multiply that second row by I, Remember, row operations don't change the null space, so the null space will be the same. So we'll have the null space of I1 minus I minus 1 because I squared is -1. Now we can add the first row with the second row and make that become our new second row. Row operations don't change the null space. And so that gives us the null space of I1, 0, 0. And then maybe if we really wanted to, we could multiply this first row by -I just to clean it up a little bit. That'll give us the null space of 1, -I, 0, 0. And then this is technically in reduced row echelon form. So the null space of our original matrix, which is the eigenspace for lambda plus, is the same thing as the null space for this row reduced matrix. Now we can analyze that. So let's suppose that xy is in the null space. So let's write it like this. So if xy is in that null space, so that's 1, -1, 0, 0, that tells me that 1, -I, 0, 0 times xy is equal to the 0 vector. That's what it means to be in the null space. But that means that x minus iy is equal to 0, which means that x equals iy. Again, we did some matrix vector multiplication. Now we can take a free variable, which is y, set it equal to 1. And then that means that x is equal to I, which means our first eigenvector, which I'll call v plus to be in line with this lambda plus, is equal to I1. Okay, nice. And in fact, our second eigenvalue, which is attached, or eigenvector, which is attached to lambda minus, will be the complex conjugate of that. So that follows from some results from an elementary linear algebra class. Okay, so let's bring that data to the top, and then we're finally ready to diagonalize. Okay, we determined that the eigensystem of our rotation matrix has the following eigenvalues and their corresponding eigenvectors. Now we can find a diagonalizing matrix using these eigenvectors and then a result from linear algebra. So let's maybe set P equal to the matrix whose columns are these eigenvectors. So we've got I1 minus I1. Great. And then we'll also need P inverse. So remember that P inverse will be 1 over the determinant and then some switches of elements in here which we'll go through. So let's see what the determinant is. So it's going to be I times 1 minus -I times 1. So that'll be 1 over 2i, which is the same thing as minus I over 2. So like I said, that's 1 over the determinant here. And now we swap the diagonals. So that's going to give us a 1 here, an I here, and then we negate the off diagonal. So that'll give us an I here and a -1 here. Then maybe we'd like to multiply this through a little bit. So that's going to give us, let's see, minus I over 2 here, 1 over 2 here. We have I over 2 here, and then another 1 over 2 here. Okay. Now next, we know, this is a fact from linear algebra, that P inverse times our rotation matrix times P will be diagonal where the eigenvalues are on the diagonal. So here, the eigenvalues being on the diagonal correspond to how we chose the columns here. So we'll have e to the I theta here. We'll have 0, 0, e to the minus I theta here. So I'll leave this calculation maybe as a little homework exercise, and we'll move on to the visualization of our original rotation and now this new diagonalized rotation. So we just got done diagonalizing our rotation matrix. Now I want to give you finally my trick for visualizing this diagonalization. So here's how I think about it. So if we take just 2 copies of the complex plane, so this is C2. So this axis is a complex axis. This axis is also a complex axis. So in total, this is a 4-dimensional real space. So that makes it pretty hard to visualize, but that's kind of the trick of this diagonalization. So here we've taken our basis to be the standard basis. So we've got this is in the direction of 1, 0. So obviously the unit vector stops wherever we tell it to, but that's the direction of 1, 0. And this is the direction of 0, 1. Okay, so again, recall that this was our rotation matrix. We've got cos theta minus sine theta, and cos theta. And also recall that the action was something like this. It took a vector v and it rotated it by an angle theta, and that rotation occurred without changing its modulus or its norm. So the length stayed the same. So here we have, this is angle theta, and this length is the same as this length. So that was like the first half of the video, we made that calculation. And you can actually visualize this as rotating the entire plane like this. Okay, so now what's going on over here? So here we have changed our basis to a basis of eigenvectors. We've got I1 and minus I1, and now we've got a diagonalized matrix. So now let's get a vector up in this plane. So I'll say the vector is V again. And now if we multiply by this matrix, exactly what changes? Well, it's hard to visualize, but let's recall that this vector is a two-dimensional complex vector. But let's recall that this vector spans a line, a one-dimensional complex line, but that one-dimensional complex line is a two-dimensional real space. And so, in fact, what we've done is we've pushed the rotation into something that's happening along this line. So what's really happening is really the rotation is just happening within that line. And in fact, that's happening everywhere. So if we were just to multiply along a vector that runs along this horizontal axis, it would rotate along its axis. The same thing up here, it would rotate along its axis. So there still is some rotation that's occurring, but it's just occurring along the axes of the vectors. And that's a good place to stop.